The Advanced Photon Source at Argonne National Laboratory is a state-of-the-art national research facility funded by the U.S. Department of Energy. It is designed to produce extremely brilliant X-ray beams for basic and applied science across a wide range of scientific disciplines. The APS generates brilliant X-ray beams by accelerating and storing charged subatomic particles. The process begins with an electron gun, a cathode ray tube much like the one found in a television. Electrons produced here are injected into a linear accelerator, or LINAC, where the energy of the electrons is raised to 450 million electron volts. Next, the electrons are injected into the booster synchrotron. Within this racetrack-shaped ring of magnets, the electrons achieve an energy of 7 billion electron volts, nearly the speed of light. The electrons are then injected into a 1,104-meter-long circle of magnets called the storage ring, which is located inside the experiment hall. Each second, the electron beam travels more than 271,000 times around the storage ring. The storage ring and the experiment hall are divided into 35 sectors. Each sector has two beam lines that extend as much as 75 meters from the storage ring enclosure into the experiment hall. One of the beam lines in each sector begins at a bending magnet, which produces radiation with a broad distribution of energy. The other beam line begins at an insertion device. Insertion devices are arrays of powerful alternating pole magnets. They are central to the enhanced capabilities of the APS. As the beam of subatomic particles passes through the alternating magnetic fields from the insertion device, the particles change direction very rapidly, creating pulses of invisible light in the X-ray part of the spectrum. This pulsed light has great intensity and is highly concentrated in the forward direction. X-ray beams that can be hotter than the surface of the sun flash down the beam lines, which lead to research stations. These stations contain the material to be studied and detectors that collect data from the interaction of beam and sample. 50 meters from their source, a wide band of X-rays from the powerful APS enters the primary aperture. This small opening eliminates unwanted radiation outside of the main beam and defines the geometry of the beam. It also eliminates most of the heat from the initial X-ray beam. The beam next encounters a monochromator which contains two silicon crystals, one flat and one bent. The first flat crystal precisely selects the X-ray wavelength, or energy, that the experimenter wants to use. The second bent crystal focuses the beam horizontally. Each beam line can be equipped with two monochromators with slightly different spectral properties, but only one is needed at a time. Next, the beam strikes a bent mirror at a glancing angle. At these energies, X-rays reflect smooth surfaces if the angle is sufficiently shallow. The bend of the mirror focuses the X-ray beam vertically. At the end of the beam line, the optics are able to deliver a stable, intense, highly focused but physically small X-ray beam with low angular divergence onto a sample mounted in front of a detector. This detector gathers information from the interaction of beam and sample, processing that data onto a sample mounted between the X-ray beam and a detector. This detector collects large volumes of data quickly and accurately and saves it for interpretation by researchers. Each sector on the APS experiment floor is managed by the scientist in one of the teams of researchers, in effect creating a multitude of individual laboratories at one facility.